You ever wonder what cathodic protection criteria is? Sure, you can read about it, and that is helpful. But here at Corrosion Coach, we're going to talk about it at practice and get you ready for game time. We're also going to talk about those pipe to soil potentials that you keep hearing about. Certainly, those are associated with that CP criteria. So let's get you going a little bit. You all know from probably the past or in one of my previous videos what cathodic protection is. What I'm showing you on this screen is we've buried our own anode material. We've attached it on the positive terminal of an energy source. In this case, it's a rectifier. And we're going to drive current off of those anodes, that sacrificial material, through the earth. We're going to collect it on our pipeline, and then it's going to be connected via a negative connection, and it's going to go back to that rectifier. So again, we're in the clockwise position today. This is what we call a cathodic protection system. So instead of the current discharging off of our pipe in this case, it's discharging off of the anodes. We got all four components. The anode is the material we buried. The cathode is the pipe itself. The electrolyte is the earth. And the metallic path is kind of a combination of things, but it includes that cabling that we connected via the negative and via the positive. Well, great, fine. We've got a CP system now. I'm feeling pretty good about it, but I can't just set it and forget it. I've got to go prove that we're meeting criteria. Another way to put that is I've got to go prove that I'm achieving cathodic protection. I am not corroding. So how in the world do we do that? The most basic thing that we do is something called a pipe to soil potential. Again, you'll hear us refer to that a couple different ways. Usually you hear pipe to soil. Sometimes you'll hear structure to electrolyte potential. If you hear that, don't let that throw you off. It really means the same thing. Just replace structure with pipe and replace electrolyte with soil. Those things mean the same thing. So what we're going to do is we got to go measure this pipe to soil thing. So we're going to want, let me get my laser pointer for you. We're going to want a digital voltmeter. Okay. Usually that comes in the form of a multimeter, and you have a dial on it or a setting, and you can get over to volts DC. And so we're going to use that meter. You're going to hear me ask you to make sure you're using a high input impedance digital voltmeter, a 10 meg ohm or greater digital voltmeter. That comes into play a little later. But we're going to use that voltmeter, and we're going to attach the red lead or the positive lead to the pipe, which is shown here on this drawing. And then we're going to attach the negative lead or the common lead or the black lead to a reference electrode. Now you got a couple options with reference electrodes. There's different ones out there depending on the environment you're in. But usually here on land, if we don't have any kind of issues, we're not in salt water, we're going to use what's called a copper sulfate reference electrode. And there's a couple different brands out there that you can purchase them. But we're going to make sure that's a calibrated reference electrode. So again, the red lead is what we're attaching the pipe to. The black lead is what we're attaching the reference electrode to. And so we're going to take red lead pipe to soil electrode potential. And that's going to give us a voltage measurement. That's a DC voltage measurement. And so we're looking for a certain number, and we'll get into criteria here in a second. We're looking for a certain number, and that's going to tell us whether or not we're achieving CP or not. This is where I usually stop and compare. It's a very common measurement for us to just kind of get a good yes, no, how are we doing on our pipeline? Are we achieving CP or not? You're going to see later that there's all kinds of error in that, but I kind of compare it to the medical industry. Not that we're doctors, but I kind of compare it to the medical industry. What do you do when you go to the doctor? First thing they do, they're going to take your temperature, they're going to weigh you for some reason, and somewhere in there, they're going to take a blood pressure measurement. That's kind of the same thing as our pipe to soil. It's kind of a basic check. Are we good or not? Is my blood pressure high or low? And so I kind of compare it to that. If your blood pressure is high, it doesn't necessarily mean you have a problem. you may have to have further tests conducted to see if you have a problem. There's a lot more questions that the doctor is going to ask you. It's kind of the same thing for us. So it's a very basic measurement. It's extremely important. It is regulated, and I'll show you that in just a minute, but it is kind of a basic yes, no, how am I doing type measurement. That's a pipe to soil or a structure to electrolyte to prove cathodic protection or not. So we do have some regulatory requirements involving making sure that we not only have cathodic protection on some of our pipeline systems and other structures, by the way. That could be a tank, it could be a well, it could be many things, but so common, it's a pipe. But we do have regulatory requirements. That could be at the federal level, that could be at the state level, could be at the local level, meaning the city or the county. So you do kind of you got to pay attention to all of those. And then you may have a company procedure that supersedes all of those. And get that out of there. So when we talk about federal regulatory requirements, we've got a couple different codes. I'm not going to bore you with the regulatory requirements. You can go do that and hang out on the weekend and go read that. But when you talk about natural gas, that's going to fall under Code of Federal Regulations, Part 192. There are many subparts to that. And so there is a section in there for corrosion control, and then you get into cathodic protection. That's going to be for natural gas. When you get to liquefied natural gas, that's going to be 193. And then when you get into hazardous liquids, that's going to be 195. Now, they're all, I hate to say they perfectly agree on cathodic protection, but they're pretty close. There is some subtle verbiage differences, so you do need to make sure that you understand it depending on what asset is regulated that you're trying to manage, so that you understand that cathodic protection criteria and what it is you need to do. But they are all similar, okay? But just don't make the mistake of saying, oh yeah, they all say the same thing. Not so much. Be a little careful, but they are similar. Do we have any help from the industry? So if the federal government's going to say thou shalt do some stuff, do we have anything in the industry that can help us out? Sure we do. I'm a member of AMP, formerly known as NACE, and they issue standards from time to time that help us specifically with corrosion control and cathodic protection for underground or submerged metallic piping systems. Okay, so there's all kinds of other standards out there. This is this is the standard for pipelines, SPO or SP0169. Then you'll see a dash, and you're going to see a year after that 2024. That 2024 is the last iteration of it. That's live action news. I'm in 2025 right now, talking to you at the time of this video. The last iteration of this, or last version of this, was updated in 2024. Typically, there's not wild major changes. If there is, there's quite a bit of buzz in the industry about it, but there are going to be some subtle differences here and there. So you may have a previous version you're working on, and be careful, because the regulatory agencies, they may not point towards 2024. They may still point towards a previous year, for example, 2017 or 2013. Your company procedure may point to a specific year as well, and a regulatory requirement may not point to it at all. It may just kind of spell out an old one. So just be careful of that. But I do encourage you to get your hands on that standard. If you're a corrosion control professional, you should be a member of AMP. You're probably certified through AMP. I'm an AMP instructor. I highly encourage you to do it. It is fantastic. And if you are a member of AMP, formerly known as NACE, then you do have access to these standards. SP0169 is one that you just want to have on you, and just make sure you refer to it from time to time and get to know how to read those things. Don't be scared of it. Go straight into it. And then the other, it's not really a standard, it's a TM. That stands for test method, but it really goes hand in hand with the standard. AMP puts this out as well. I think it's currently listed as NACE, but you can get it on AMP's website. The latest version of that is 2022. So you've got the TM0497. That's going to offer you different measurement techniques related to that criteria. So it'll talk about how to take that pipe to soil in more depth, even more than this video, and it'll talk about all the errors associated with that simple, basic blood pressure measurement. So enough about regulation and standards. You can pause this. You can go look this up yourself. I just wanted to give you a little bit of heads up. So let's talk about that pipe to soil potential a little bit more. Surely it can't be that hard, right? It sounds pretty easy. I got a meter, I got a reference cell, I'm attaching to the pipe, taking a pipe to soil, and I'm going to get a certain measurement. And I'm going to see if I'm achieving CP or not. So this is kind of an excerpt out of that criteria, the SP0169, and I'm simplifying it somewhat. So what it's going to tell you is this. Okay, I'm going to get my magnifying glass and see if that's a little better. So the first part of it is it's going to say, hey, look, I want that measurement on that meter to be a negative potential, so a negative number of at least 850 millivolts with respect to CSE. CSE stands for copper sulfate electrode, okay? So I need a negative 850 millivolts to read on my meter with respect to that copper sulfate reference electrode. But it's got a couple bullet points. So we can't just stop at, hey, I got a negative 850 millivolts, I must be good. That would be too easy. Instead, we got to kind of read those bullet points. The first bullet point says, hey, that needs to be a direct measurement of something called a polarized potential. What the heck is that? And so they've added some complexity to it. And then the second bullet point says, that could be a current applied potential, meaning your current sources are on, your CP system is on, but even that's got an asterisk next to it. All right, well, let's go down and look at what the asterisk says. So it says that interpretation of a current applied measurement requires consideration of the significance of voltage drops in the earth and metallic paths. What happened to my minus 850 and I'm good to go? That ship sailed. So we're going to dig into that a little bit. We're going to kind of break that apart, but we've got these voltage drops we got to consider. We got to think about it. And those voltage drops can be in the earth and they can be in the metallic paths. Okay. The other part of the criteria, some people call this the alternate criteria. It's not really alternate. It's just another criteria. You can use this. It's something called 100 millivolts of polarization. So if you can prove 100 millivolts of polarization or buildup of polarization, you're good to go. The other way is to turn your system off and watch it depolarize or decay 100 millivolts or more. You're good to go. You've achieved CP. So they're giving you options on how to check your blood pressure and make sure that you're in line. Once you practice it, once you get used to this, kind of read through it, hopefully this presentation will help you. I think it'll become kind of common knowledge for you. So let's jump in and kind of explain that a little bit. Let me get this turned off here for you. You're going to hear us talk about something called an on potential. We may call an on would be with our CP system turned on. That's all we're saying. We may call that something else. Again, we're trying to confuse you. AKA, we may call that an applied potential. It means the same thing as an on. We may call it an energized potential. Those are the common ones I hear. There's probably some other terms out there, but those are the common ones I hear. Heck, I say current applied potential sometimes instead of on. But I don't want you confused. Those are just some other terms there to kind of help you out. You'll hear us talk about something called an off potential. We'll call that all kinds of things. We'll call it an instant off, an IR free potential. You may hear us call that a polarized potential. There's that word again. And by the way, there's a little short definition for you on polarized potentials. I don't want to spend a ton of time on polarized potentials in this presentation. We'll create another one for that. And then we'll talk to you about native potential. That's the potential of the steel structure, the pipeline, before you even put cathodic protection on. It just, as is, it's out there. That's a native potential. We'll call that different things. Native state, natural, static. I hear that quite a bit. I use that. Free corroding. I don't use it as much, but it's out there. Rest potential, open circuit potentials, certainly something you'll hear, especially as you progress through CP1, 2, 3, and 4. You're gonna talk about open circuit potentials quite a bit. So just kind of get used to those. You might snapshot this. You may come back and refer to the video, note it, put it up on your board if you're taking a course or something like that. All that means the same thing as native. Okay, you will see this curve from time to time. I have. Certainly academically, you're going to see it. I think in every CP course I've taken all 4. I've seen it, and you do get very used to it. This particular graph came out of Peabody's book. You've heard me talk about that before in my presentations. That was my college book, and it's a great read, good resource to have. But this came out of that, to give them credit. So what we've got here is we've got a graph, and on the vertical axis here, we've got negative voltage measurements on the top. We've got more positive or electropositive measurements on the bottom. And then the horizontal line represents time, is all that is. And so when we have our rectifier on, or our CP system on, we're going to measure that pipe to soil potential, and it's going to be the most negative reading it's going to be. That's one way to think of it. And so it's going to be extremely negative. But we can't, according to the standard or criteria, we can't just take that reading. They told us we have to consider voltage drops. And so one way to try to tackle that is to conduct an instant off potential survey. And so what we're going to do is we're going to turn our rectifier off, and that's going to drop that number more electropositive, actually, and it's going to give us something a little cleaner, something without error in it. And this should come to light here in a minute, but it's going to get rid of some of that error. We call that IR error, current times resistance, and it's going to give us a cleaner potential, an off potential, a polarized potential. And so if you go back to that criteria, you might be able to use this to prove cathodic protection. So keep that in mind. Now, what this graph is showing you is if I leave that rectifier off, or that current source off, that potential is going to continue to get more positive, more positive, more positive over time. Remember that 100 millivolt shift, that 100 millivolts of decay? Whatever this number is, if it decays or depolarizes at or more than 100 millivolts, we've achieved CP. So that's another way to prove cathodic protection. It's not always practical, but it is a method. The other way is, remember the native, this dotted line? We talked about native. That's when the pipe, before it had cathodic protection on it, pipe in the ground, they buried it, go take a bunch of potentials on it. That's your native state survey. Those are your native state pipe to soil potentials up and down that line at those test stations. So that's going to give you some kind of number. Once you install CP and energize it, if you can conduct an instant off survey, or a polarized pipe to soil potential, and the difference between that and that native potential is at or more than 100 millivolts, you've achieved cathodic protection. So again, I'm giving you a lot of information. Make sure to snapshot this thing. It's got a lot of information on it. We'll see if we can't make sense of it here in a second. That test method, I kind of mentioned it earlier. It's another go-to. I think I would grab it. It's a great companion to the standard. It does list, we talked about error in that reading, that blood pressure reading, pipe soil reading. It does list greater than 20 sources of measurement error. Those are just identified ways that we can introduce error into that measurement. A lot of the ones listed are really easy to overcome. Some of them not so much. So just kind of keep that in mind, but great reference for you, especially if you're a corrosion control person. It's like, get a hold of that and get to know it. Okay, so back to this is the same slide I showed you earlier. Just a reminder, we're looking for a negative potential of 850 millivolts. That can be a direct measurement of a polarized potential, instant off, possibly. It could be a current applied potential, but it has the asterisk. That means I got to interpret that current applied potential. I got to look at the significance of the voltage drops of the earth and the metallic paths. all right? And then 100 millivolts is the off minus the native is one way to do it, or off, leave it off, decay at or more than 100, and you're good to go. So that is a decay of polarization or a buildup of polarization, whichever way you can prove it. Okay, we got a busy slide here, so I'm going to slow you down intentionally. We're going to just kind of take a look at this. Let me get you a little bit bigger here. There we go. Okay, so over here, I've got my rectifier, and I've got my positive terminal, my negative terminal on my rectifier. Positive is always going to be on the anodes, or whatever you want to corrode. Negative is always going to be on my pipe, or whatever you want to protect. Keep that in mind. The rectifier don't care. Whatever you put on that positive side, it's going to corrode it. So what we've done is we've installed our anodes on the positive side, and those anodes, they're blue today. We showed that to you earlier. It's going to produce blue current, okay, through the earth, and it's going to collect on our pipeline in various locations all up and down the pipe, all right, not just in one spot. And then it's going to use the pipeline here as a metallic path, okay, because that's going to help it get back to the rectifier. And then as it approaches the rectifier, it's going to use this negative connection or this negative cable to get back home. And then we're going to go down the positive side again, off the anodes, corrode the anodes on purpose, through the earth, collect on our pipe, round and round we go. Now, one thing I did to you here, I don't know if you noticed it, but I've got these small blue arrows with yellow trim, and that represents current, and it's a relatively small amount of current, okay? As it builds up on the pipe and gets closer to the rectifier, the magnitude of that current gets higher. It's more current, DC current we're talking about here. And so that's being represented by the size of the arrows. So the largest amount of current is going to be closer to that negative connection. Just kind of keep that in mind. That was a little feature I put in there for you. Okay, so I've got my CP system going. All right, I've got to show up. I got to take this pipe to soil potential, and I got to prove if we have achieved CP or not. Okay, so I've got my fluke meter up here. I've got my red lead connected, my positive lead to the test station. The test station's connected to the pipe. Okay, we usually weld some cables on for that. And so that's my connection to the pipe. And then I've got my black lead or negative lead connected to my stationary reference electrode. In this case, it's a copper sulfate reference electrode. That's a Tinker and Razor picture, by the way. Shout out to those folks, good people over there. So I'm going to take my pipe, red lead, test station, to soil, black lead, reference cell. When I do that, I'm going to get a number on my meter. It's a voltage number, okay? It's DC volts. I got to make sure I'm on DC volts on my meter. It's going to be a negative number. That's a normal operating condition. And again, according to that standard, we're looking for that negative 0.85 volts or negative 850 millivolts. That means the same thing, okay? That's what we're looking for. Now, we got to interpret that a little bit because we have metallic paths error that we're dealing with. We've got earth error that we're dealing with. So we got to think about that a little bit. So right here in the middle, this text that I've inserted is the metallic path considerations. It's the measuring circuit as a consideration. That would be the meter itself. It may have some kind of resistance in it. It could be the cabling or wires that we use. It may have some kind of resistance associated with them. Sure, they're made of copper, but there could be resistance, right? And then the structure itself. Remember, I've got current traveling on a pipe. The pipe is part of the metallic path. And then the cabling in the negative and positive. And so I've got all these opportunities to have error in my measuring circuit. Now, what I can tell you is on the meter, we take care of that by using a high input impedance multimeter, okay, or voltmeter, high input impedance, and then we make sure we use appropriate cabling, and that assists us in basically eliminating any error with a measuring circuit. The only other thing you got to look at is where you put your reference cell, because we stick that thing, it's got a porous tip on it. We stick that thing in the ground. Well, if you're in a rocky environment or sandy environment, you can really add resistance just by that earth contact, and it can really make you scratch your head on your reading. Is it right? Is it not? Chances are it's not. So you want to kick that dirt down and get to something with moisture in order to get a little bit more accurate reading. You can actually pour water in order to do that. So that is listed in that test method, and that can be a spot that you can have plenty of error. So just be advised of that. Make sure you got good earth contact with your reference cell. But that's our measurement circuit. The structure itself, that's a little tougher to deal with. What can happen to you is if I move this reference cell out further away and further away, feet, maybe even miles down the pipe, but I'm still connected back at this test station, there's an introduction of error in that measurement, okay? It's less about the actual measuring equipment and cabling, and it's more about the structure itself or the pipe itself, because remember, current is gathering on it and it's using the pipe to travel down. So as we get further away from that test station with our reference cell, have cables still hooked up, there's a method called close interval survey that we see this all the time. We are going to increase our error in that pipe to soil measurement, so that negative 850 millivolts that we measured may actually not be correct at all. It may be way more negative than it actually is. So just keep that in mind. That's the structure. Then we have the earth that we have to talk about. Well, the earth acts like a resistor as well. And we've got current traveling through that resistor. A gradient or a voltage drop is simply I times R, current times resistance. Current traveling through a resistor, that's a voltage drop. So anytime we have current traveling through the earth, we are increasing the error in this measurement that we take. Okay, well, let's get to the whiteboard and see if we can't make a little more sense of this. So I'm going to go ahead and pre-apologize for my drawings once again. But I've got the illustration up here in the top left corner, so you can kind of quickly refer back to it. It's a little bit cleaner, but I've really tried to replicate that. I think it's exact. I don't know about you, but it looks exact. But I've tried to replicate that for you here. So I've got my rectifier over here. I've got my blue anodes hooked up on the positive. I've got my negative connection here on the pipeline. My meter is here. My reference cell is on my black lead. Red lead is connected to my pipe via the test station. You can see the test head with a couple leads connected to the pipe. Why 2 leads? For redundancy, in case one breaks. So I'm looking for, when I do this, I am looking for a negative 0.85 volts, or same thing as saying this. Those are the same numbers. So negative 0.85 volts or negative 850 millivolts, that means the same thing. But that's what I'm looking for. But I have to consider the metallic the structure, the metallic path, and I have to consider the electrolyte, okay? So again, our measurement circuit is taken care of with a high input impedance meter, proper cabling. My pipe itself, I'm going to take a pipe to soil directly over the pipe at that test station. It's going to be a little more accurate than moving my reference cell out, obviously. And that's going to take care of my metallic path. Now let's talk about the earth. So again, we have blue current gathering on this pipe. Okay, that's what we want. And then as it gathers, it's going to use the pipe to travel, and then it's going to use this negative connection. Well, if the blue current is I, and the earth itself has resistance, that means I have IR error in my measurement. So I cannot trust this 850 millivolts. I can't. And so one thing I can do is say, well, turn my blue current off. Oh, okay, let's do an instant off potential. So I'll go over there, or have an intern or somebody that works with me or something, go over there and turn this rectifier off, and I'll take a measurement as soon as I turn it off. Then it's going to give me some kind of number. Okay, that number, because I've taken I, so mathematically, if V equals IR, and I take I and make it 0, 0 times anything is 0. So the thought there is if I take it to 0, I've eliminated IR error or voltage drop error, and now I can trust that measurement. In a lot of cases, we can do that. When we're the only ones out there in the right of way, it is no problem. However, let's pretend, I'm gonna make this complicated on you. Let's pretend we got a friend close by and they've got their own CP system and their own pipeline, and their anodes are more red, and their red current is kind of passing through town here. It's not collecting on our pipe, but it's passing through the same earth. It's passing through the same electrolyte. If I just turn off my blue current and take a measurement, have I eliminated the voltage drops? Unfortunately, no. If red current is on, no, we haven't. Aha. Okay, well, let's call him and see if he'll turn his rectifier off as well. Maybe we can turn them off and on at the same time and get those measurements. That's possible. So we can eliminate that red current. All right, let's complicate it even more. Let's pretend that when this pipe was first constructed, maybe they buried some magnesium anodes and they directly buried it and connected it to the pipe. And maybe we don't know where those anodes are. Well, as soon as I turn my blue current off and even my friend's red current, what's going to happen to these green anodes? They may produce green current. Yikes. So that means that my instant off is no longer off again. I did not consider the voltage drops in the earth. Okay, well, let's say we dig those up and we cut those out. Let's pretend that our pipe system is actually connected. It ties in at a compressor station. And that compressor station has a very sophisticated grounding system. And let's say that grounding system is copper. If you go to my galvanic series video, you'll know that copper is more noble than steel. In other words, steel is more active than copper. The more active metal is going to corrode, produce current, to protect the more noble metal. And so if I turn my blue current off, my red current off, I don't have green current anymore. If I'm shorted to a copper station, my steel pipeline may corrode to protect my copper, which produces, we'll just call that black current, back to the grounding, which means I'm going to have error in my reading there too. So I'm overcomplicating this on purpose, but this is, really it's reality. There's a lot of folks out there that they're going through this. They're feeling this pain, and they're like, how in that simple pipe to soil potential, gosh, man, it just became not simple. What do I do? So what we can do, there's a couple things. All right. There's no perfect way. I'm sorry. There's not a perfect way, but there's a couple things you can do. Okay. I'm a fan of installing, I got to find another color. Let's go purple. So what if we installed a drop tube? And that's typically PVC. And we may fill it up with soil here and perforate the bottom. But if I have a drop tube in which I'm able to drop my portable reference electrode down in it, it's got a cap on it, and I can get down closer to the pipe, think 6 to 12 inches off the pipe, that might be optimal. But if I can get closer to the pipe, I can get past all that current that's traveling through resistors, all those voltage drops. If I can do that, I can eliminate a lot of that error in that measurement. And now I can trust that my measurement on my voltmeter is cleaner data. It's more accurate data. So I'm able to make better decisions. That's one way, a drop tube. The other way is to install a stationary reference electrode. Again, 6 to 12 inches off the pipe, maybe at the 5 or 7 o'clock position. And he lives down there, and we bury it next to the pipe in the same soil and all that. And he lives down there. And every time I walk up, instead of hooking up my portable reference, my reference is already there, AKA a stationary reference electrode. So I take a pipe to soil. Wouldn't that be more accurate? It absolutely would. Now, do they last forever? No. That's why your corrosion coach is a little more of a fan of a drop tube, but they both work. I've done both. And so again, there's no perfect solution, but there are some things you can do to help determine a more accurate measurement. Okay. Especially when you're busy in a busy right away. You got red current, purple current, green current. I sound like the Lucky Charms cereal now. But when you have that, you do have to be creative. And a lot of my friends in the business, they're doing this and they're doing a wonderful job of it, but it's an uphill battle sometimes. But once you get some of this stuff kind of set out there, man, it makes it a lot easier to determine, am I achieving cathodic protection or not? So again, not to compare us to doctors, but in a way, yeah, you do want your doctor to understand what's going on. You do want him to understand the error in all the testing that they do to us. That's the kind of doctor I want. I want somebody that can kind of look at that and go, I don't know if that's a real reading. And he's going to determine another test and another test to be a little more accurate. He's going to ask good questions. We need to do that as well. So a little bit long-winded on this one. I'm definitely passionate about this one. I think if you're going to be a corrosion control guy, especially a cathodic protection guy, whether you're a technician, or you're somebody who's managing techs or managing assets, maybe you're part of the integrity group, whatever it is, this basic thing, really, we need to peel this onion back. We need to understand. It's going to make you're going to like it. Okay. If you get into this and you understand it, you're going to like it. You're going to be better off. You're going to prevent corrosion from happening. You're going to have a higher likelihood of that. So it's going to be a really good thing. So I appreciate your time. Look, we had a good practice this round. I could feel it. And I think that we are better prepared for game time. So I'm your corrosion coach, Adam Johnston. Can't wait to see you next time.